Right. So the last time I saw you guys, I was talking about the properties of acids and bases, went through one of the definitions of acids and bases being Arrhenius. And I'm going to build on that today. So we have Arrhenius. Acid is an aqueous solution that increases the concentration of hydronium. And because we've already studied concentration, remembering that, I'll let that in. Okay. Okay, and then now that went away, of course. So we've got Arrhenius. Oh my goodness, okay. There's some, hold on a sec. Nope, go back. All right, Selma's here. Hold on a second. Still waiting for 5, huh? All right, anyway, go back, yeah. See if I can do this again. So, Arrhenius defined an acid as an aqueous solution that increases the concentration of hydronium. Remembering from our chapter on concentration, where a square bracket means concentration in molarity, which is big M, and an Arrhenius base, again, is an aqueous solution that increases the concentration of hydroxide. So that was the first acid-base definition. Now today, I'm going to go through the other 2 definitions of acid and base, and then we can start to look at how we define acids and bases based on reactions and what's happening. So after Arrhenius, scientists were investigating acid-base behavior, and they found that some substances acted as acids or bases when not an aqueous solution. So if that's the case, then Arrhenius's definition is not accurate enough. So, sorry, Frank's here. Hold on. Okay. Make sure I mark him present. All right. Oh my goodness. There's Beam. Problemo. I feel like every time I get started, I'm like, boop, there it is. All right. So again, Arrhenius' definition of acid and base requires aqueous solutions. So we have to revise our definition of acid and base. It doesn't mean necessarily that Arrhenius is wrong. It's just a different way to define acid and base. So the most commonly used definition of acids and bases is the Bronsted-Lowry definition. And this is based on the transfer of protons. So a Bronsted-Lowry acid is a molecule or ion that is a proton donor. Okay, that's going to be the key, a proton donor. Now, I want to remind you that a proton is also can be defined as a hydrogen ion, because hydrogen has only 1 proton and 1 neutron, or sorry, 1 proton and 1 electron. So when hydrogen becomes an ion, it loses its 1 electron and it is literally just a proton. So anything that donates a hydrogen ion or a proton is considered a Bronsted-Lowry acid. Okay. Now it's important to remember during this unit that when I'm asking you to apply definitions, you have to think about each definition separately. Now, I did mention last week that in one single chemical reaction, You cannot have both both an Arrhenius acid and an Arrhenius base, because you're either going to be increasing hydronium concentrations or you're going to be increasing hydroxide. You do not see reactions where you increase both, because guess what that does? That just produces water, which is why you don't have in a chemical reaction Arrhenius acid and an Arrhenius base. However, when it comes to the Bronsted-Lowry definition, because you're talking about a molecule or ion that is a proton donor, that means that in the reaction, there must be a proton acceptor. So for Bronsted-Lowry and for the third definition, which is Lewis, you have to have both an acid and a base in each reaction, because you have a transfer of something happening. So for Bronsted-Lowry, it's a proton. Now, Arrhenius acids are defined as aqueous solutions where you're increasing the concentration of hydrogen. So because the hydrogen ion is a proton, all Arrhenius acids donate a proton, so they're also Bronsted-Lowry acids. So if you can apply the Arrhenius definition to an acid, you automatically apply the Bronsted-Lowry definition as well. So there will be some shortcuts that are based on logic and being able to figure out, like, well, if A is true, then B must also be true. Substances other than molecules can also donate protons. So these are not going to be considered Arrhenius acids, but they will be considered Bronsted-Lowry acids. So you can say that all Bronsted-Lowry acids are, I want to make sure I say that. No, I want to say that the correct way. So ignore what I just said. All Arrhenius acids are Bronsted-Lowry acids, but not all Bronsted-Lowry acids are Arrhenius acids. Okay, so I'll say that again. All Arrhenius acids are Bronsted-Lowry acids, but not all Bronsted-Lowry acids are Arrhenius acid. Bronsted-Lowry is a broader definition, so it will include more substances. So let's look at an example. Hydrogen chloride, when it's dissolved in ammonia. And this is what I was talking about last week when I said that you have to look at the products to determine what had happened. Remember when I talked about that? You compare the reactants and the products and you say, okay, what actually occurred during this reaction? So I started with HCl, and I started with HCl and I ended up with Cl. So what happened? HCl donated a proton to ammonia. So if you go, which created then NH4. So you look at NH3 became NH4. So NH3 got a proton, which is a hydrogen ion, from HCl. This makes HCl a Bronsted-Lowry acid, simply because it donated a proton. Okay. Now I can also then say that that makes the ammonia a Bronsted-Lowry base, because guess what a Bronsted-Lowry base is? It's a proton acceptor. And I just so happened to pick red and blue for these. It's like matches their indicator colors. So this is a proton donor. And that's it. That's the only thing that defines a Bronsted-Lowry acid and base, on whether or not it accepts a proton or donates a proton. So every time I give you an equation and I say, does Bronsted-Lowry definition apply here? You're just going to say, did something donate a proton? If it did, then it absolutely applies. And then you have to figure out which one is the acid, which one is the base. So HCl transfers the proton to ammonia and it forms ammonium, which is NH4 plus, and you're left with the chloride. If you want to see it in Lewis dot structure, if you remember your Lewis dot structures, this is it. This is going to come in when I talk about the Lewis definition of acid and base. So I'll talk about that later. Okay, so I'll talk about that later. Water. So now here's where it gets interesting. Water can also be a Bronsted-Lowry acid. If you dissolve ammonia in water, look what happens. the ammonia gets a proton donated from water. So in this reaction, water is a Bronsted-Lowry acid because it donated a proton. Because you compare what happened on the other side. You start with H2O and you end up with a hydroxide, which means one hydrogen was donated. That makes water the acid. And again, same thing here. Ammonia accepted the proton and became ammonium, which makes it the base. But you have to remember that the acid and base pair are always the reactants. I will get to what the products are a bit later, what we call those. So again, Bronsted-Lowry base is a proton acceptor. And again, with the reaction with hydrogen chloride, the ammonia accepted the proton from HCl, so it is a Bronsted-Lowry base. And this is why in the Bronsted-Lowry definition, you always have to have an acid and a base because it's a transfer. Now, one of the classes of Arrhenius bases that I mentioned last week were the metal hydroxides, like sodium hydroxide. It's not necessarily a Bronsted-Lowry base. As compounds, they are not proton acceptors. But if it is in solution, the hydroxide is a Bronsted-Lowry base because it can accept a proton and become water. So if I ask you if solid sodium hydroxide is a Bronsted-Lowry base, you would say no, because this as a compound is neutral. It's not going to accept a proton. But if you dissolve it in water and it dissociates and you get sodium ions and hydroxide ions, this is absolutely a Bronsted-Lowry base because it can accept a proton from something else. I hope that makes sense. Okay, so this is just an old video which doesn't play anymore. But you see the Bronsted-Lowry acid on the left, and highlighted in red is the proton that's going to be donated. And this is the reason why when it's donated, you only take the hydrogen, you leave the lone pair there because it's a hydrogen ion. It's just a proton. And so what you're left with is Cl minus, and that's going to have a full octet. And then this being just the proton is going to sit right there and form ammonium. So it becomes positive. So in this example, you can see that ammonia, the nitrogen is donating both electrons to hydrogen to share. Normally, when you think about covalent compounds and how they're formed, each atom has one electron that it shares with the other. Or if you're talking about double or triple bonds, of course, you've got 2 or 3 electrons they share with each other. But just to keep it simple, normally we would look and we would say, okay, hydrogen has 1 electron and nitrogen has 1 electron, they share together, but that's not the case here. This will come back when I talk about Lewis a bit later on. So a Bronsted-Lowry acid-base reaction is where protons are transferred from the acid to the base. Now here you've got at the bottom of the screen, you can see you've got hydrochloric acid, which is HCl. And you've got ammonium hydroxide, which is NH4OH. And because it's in solution, this is going to be hydrogen ions and chloride ions. This is going to be ammonium ions and hydroxide ions. So the hydrogen ions are going to be donated to the hydroxide ions and form water. Now, the gas that you see up here is actually a cloud of ammonium chloride. So just as the hydrogen can be donated to the hydroxide, you can also have these 2 ions getting together. Okay, now based on how many acidic hydrogens are available to donate, we can classify acids based on how many hydrogens that they donate. So a monoprotic acid, again with vocab, break it down. Mono meaning 1, proton, ic, Adjective. A monoprotic acid is an acid that can donate only one proton per molecule. All of your binary acids are going to be monoprotic, like HCl, HI, HF, like that. You also have monoprotic acids in, you've got perchloric, there's one of your binary acids, and nitric. And it's really easy. You just look at the formula. If there's only one hydrogen in the formula, it's a monoprotic acid. So again, you've got even water. As I said before, water can be an acid. Water can also be a base. In this example, in this acid-base reaction, you have hydrogen chloride donating a proton to water to form hydronium and a chloride ion. So this would be a great example if I ask you what definitions of acid-base fit to this reaction. First thing that you do is you say, okay, what's happening on the right-hand side, so I can figure out what was going on. So water became hydronium, which means it accepted a proton, which means it's a Bronsted-Lowry base because it accepted a proton. And HCl, what you have left is only Cl. So HCl donated a proton, so it's a Bronsted-Lowry acid. Does Arrhenius also apply? Yes, it does, because you have an aqueous solution at the end, and you are producing, like literally producing hydronium, so you're increasing concentration. Then the question becomes, which one is the Arrhenius acid? Well, it has to match. You're never going to have something that's an Arrhenius acid for some reason become a Bronsted-Lowry base. They're not going to fit those two different definitions. So if something fits the definition of an acid, it's always going to fit a definition of an acid. It's not going to be something else as a base. So this is both an Arrhenius acid and a Bronsted-Lowry acid. Remember, the two things, the two criteria that qualify for Arrhenius is it has to be aqueous. Well, we obviously have aqueous. And for an acid, it has to increase hydronium. If you see hydronium as a product, you're obviously increasing concentration. Or in the case of a base, you're going to increase hydroxide. And this is what I was talking about last week when I said you don't have both an Arrhenius acid and an Arrhenius base in one equation. You will have either an Arrhenius acid or an Arrhenius base. However, with the second two definitions, the Bronsted-Lowry definition and the Lewis definition, which I'll talk about in a bit, you are going to have both, because it is a transfer of, for Bronsted-Lowry protons, and for Lewis it's electron pair, which I'll talk about later, like I said. Okay. Then the other acids are going to be classified as polyprotic, poly obviously meaning many. Depending on the formula, again, it could be either a diprotic or maybe even a triprotic acid if it has 2 or maybe 3 protons to give. So sulfuric acid has 2, so it's a diprotic acid, and phosphoric acid has 3, so it is a triprotic acid. It is also important to remember or to understand that sulfuric acid doesn't give up both protons at the same time. It happens in stages. So the acid will lose 1 hydrogen at a time. So for the first stage of sulfuric acid, you have H2SO4 reacting with water to form hydronium. And if you don't recall your polyatomic ion names, that is hydrogen sulfate or bisulfate. That's stage 1. And stage 2 is going to be bisulfate reacting with a second water molecule to form hydronium and sulfate. For phosphoric, obviously, it occurs in 3 stages. So sulfuric acid is a diprotic acid and phosphoric acid is a triprotic acid. So here are the 3 stages of phosphoric acid ionizing and giving up their protons 1 at a time. It is also maybe important to mention And this goes along with something I'll talk about later when it comes to describing the products on the right-hand side. But if H2SO4 is a strong acid, it means that the compound that forms after the proton is donated is weak. Okay? So they kind of do opposite. Again, I'm going to come back to the strong and weak, I think in section 3 when I talk about conjugates. All right. I really should delete those slides. All right. And then the last definition for an acid and base is from Lewis, the same Lewis where in grade 10 we were drawing Lewis structures. Both the Arrhenius and Bronsted-Lowry definition assume that acids contain or make hydrogen ions. The third classification for acids and bases are based on bonding and structure. This includes acids as substances that don't even have hydrogen. This is going to be the broadest, most inclusive definition for an acid and base. And Lewis emphasizes the role of electron pairs. And that's what I said in the previous example of ammonia, which I'll probably mention again. If an atom or a compound ion, any kind of substance, if it donates an electron pair, it is the base. And so I'm going to review all of it at the end because it's the donor and acceptor for Lewis is flipped from Bronsted-Lowry. So Bronsted-Lowry acid is a hydrogen ion donor, and a Lewis acid is an electron pair acceptor. So Lewis acid, electron pair acceptor. That's what I mean. The donor acceptor thing is flipped. So it's an electron pair acceptor. And again, just to emphasize the fact that if you have something that's a Bronsted-Lowry acid, it is, if Lewis does apply, it's not going to be a base. Okay. So just remember when, because I'll have some examples of equations and I'll ask you to apply any or all definitions and explain why. Anything that fits the definition of an acid is going to be an acid no matter what. It's not going to be an acid under one definition and a base under a different definition. That's kind of what I'm saying. Again, broadest of the three definition. Anything that can accept an electron pair to form a covalent bond is a Lewis acid. Even a single proton in a lot of the Bronsted-Lowry examples that we're looking at, going back to the HCl and the ammonia, but we'll just ignore the Cl because it doesn't actually play a part. This is a single proton. So it's going to form a covalent bond with ammonia through the donation of these two electrons from the ammonia molecule. Hydrogen ions don't have electrons to share. So that's why the Lewis definition applies. It's not, it's still a regular covalent bond, but you don't have it where one, like I said, one atom shares an electron with another atom. You've got one atom that has both electrons and it's going to share. It's like charity almost. So in this example, the hydrogen ion is the electron pair acceptor, which makes it the acid. And ammonia is the electron pair donor, which makes it the base. And again, if you look at the other definitions, all three definitions, actually, no, not all three definitions. Two of the three definitions are going to apply here. So let's just go over this real quick. Let's just say it's HCl and ammonia. It doesn't even matter if it's gas or not. And then you're going to have NH4 and chloride. So this would be a perfect example of something that I would say, okay, apply any or all definitions to the species in this equation. So first thing I start with is Arrhenius. Does Arrhenius apply? Well, again, two criteria. One, aqueous. We check that because we've got aqueous solutions on the right-hand side. In order for Arrhenius to apply to either an acid or a base, you have to either increase the concentration of hydronium, or you have to increase the concentration of hydroxide. Neither of those two ions are here on the product side. So Arrhenius does not apply. And let's just say we got Bronsted-Lowry and Lewis. Okay. So then the second definition, Bronsted-Lowry. Does Bronsted-Lowry apply? Absolutely, because you have a proton being donated to another compound. So that makes HCl the Bronsted-Lowry acid and ammonia the Bronsted-Lowry base. Third definition, does Lewis apply here? Well, I'll give you a clue. If something is a Bronsted-Lowry acid, it must also be a Lewis acid. Same with the base, because the definition of Bronsted-Lowry is donating a proton. By definition, a proton has no electrons to share, which means that if a proton is donated, it's going to accept an electron pair to form a covalent bond. So if Bronsted-Lowry applies, Lewis must also by definition apply. That doesn't mean that if Lewis applies, that Bronsted-Lowry applies. It's the same thing that I talked about before with Arrhenius and Bronsted-Lowry. All Arrhenius acids are also Bronsted-Lowry acids by definition. Not all Arrhenius bases are Bronsted-Lowry bases, because it's not about accepting protons, it's about increasing hydroxide. But specifically because Lewis deals with increasing hydrogen concentration, sorry, not Lewis, oof, my bad. Because Arrhenius deals specifically with increasing hydrogen ion concentration, it also applies. Then you can say all Bronsted-Lowry acids and bases are also Lewis acids and bases, but not all Lewis acids and bases are Bronsted-Lowry. And it makes sense if you think about it, because the narrowest definition is Arrhenius, and the widest definition is Lewis. You can always go, how do I explain that? Because Lewis is the widest definition, it means that not all Lewis acids also apply to narrower definitions. I guess that's, I don't know if maybe it's making that confusing. It makes sense in my head, I just don't know how to explain it, if that makes sense. So the formula for a Lewis acid doesn't even have to have hydrogen. I'll give you another example. A silver ion can be a Lewis acid. So here we have a silver ion, which is going to accept again with ammonia, the electron pair, and it's going to form a bond. So that means that silver is the Lewis acid and ammonia is the Lewis base. There's no hydrogen donation here, so Bronsted-Lowry doesn't apply, okay? Because there's no proton being donated. And if you were to look at Arrhenius and Arrhenius definition, yeah, you've got aqueous solution, but there's no increasing hydroxide or hydronium here. So the only definition that applies to this equation is the Lewis definition. Any compound where the central atom has 3 valence electrons and forms 3 covalent bonds can react as a Lewis acid because it accepts a pair of electrons to form the 4th covalent bond and complete the octet. An example is boron trifluoride. It is an excellent Lewis acid. It forms a 4th covalent bond with many molecules and ions. So here we have boron trifluoride. Boron is in group 3, so it only has 3 valence electrons, which means it does not have a full octet, and it will easily accept an electron pair to complete its octet. And you can see that here. So it accepted and that electron pair from, nope, let me erase that. So there's no electron pair here. It's going to accept that electron pair with the fluoride ion. The Lewis definition also applies to any species in any phase. So it can be a solid, liquid, gas, or aqueous. So the example that we looked at, actually, no, this is the same boron trifluoride, but it will also react with ammonia. Both of these are in gas phase. Again, ammonia, you've got this lone pair of electrons here, which is going to be donated to boron trifluoride. So boron trifluoride is the acceptor, electron pair acceptor, which makes it the acid, and ammonia is the electron pair donor, which makes it the Lewis base. And just again, to go through and practice with the other definitions, this is all in gas phase. So Arrhenius cannot apply because Arrhenius only applies to aqueous solutions. And Bronsted-Lowry, Bronsted-Lowry does not apply as well because there is no donating of protons. It's just electron pair. So Lewis is the only definition that applies here. Okay, I pretty much went over. Right. So this is another clue, another helpful hint. An anion is a Lewis base in a reaction where it forms a covalent bond by donating an electron pair. You'll see, I'll have a worksheet that I think we'll go over next week, I guess. Yeah. Or if I've got time today. No, I've only got 10 minutes. All right, we'll have to do that next week then. We'll go through some practice first and identifying Lewis acids and bases. But a lot of times when you see the hydroxide ion can act as a Lewis base as well because it has a negative charge. It's an anion. And oftentimes anions, they have the lone pair to share. But it's really mostly looking at what would be the acid and making sure that it doesn't have any electrons that it shares. And that is a big thing when I talked again about the Bronsted-Lowry acid base reaction is automatically Lewis as well, because by definition, a Bronsted-Lowry acid is donating a proton that has no electrons to share. So it has to be a Lewis acid as well. All right, so here again with boron trifluoride is a great example of a Lewis acid. And here fluoride is going to be the Lewis base. Again, you have an aqueous solution, but you're not increasing hydronium or hydroxide. So Arrhenius does not apply, and you don't have any proton donation or accepting. So it's not Bronsted-Lowry either. It's just Lewis. A Lewis acid base reaction, which is the formation of one or more covalent bonds between an electron pair donor and an electron pair acceptor. Even though these three definitions are different, there are many compounds that are categorized as acids or bases according to all three. So ammonia is a great example. It is an Arrhenius base because when it is in solution, I thought I was going to have a write out of the equation, but I don't. So let's do it anyway. So just like, wait, hold on. Let's just do it in water. All right. So this would be a great example. When ammonia is dissolved in water, it is Arrhenius because everything on the right-hand side is aqueous and you have the hydroxide ion there. It is also Bronsted-Lowry because it accepts a proton from water. and it is Lewis because, again, you have taken one hydrogen ion, which has no electrons to share, and it has formed a covalent bond with ammonia, so it is Lewis as well. All three definitions apply. Also notice that it is an Arrhenius base. It's a Bronsted-Lowry base. It's a Lewis base. So again, you're not going to have it switch up and become an acid for some reason, for a different definition. If it fits all three definitions, it's going to fit all three definitions for a base. So a nice little chart to summarize each of the three definitions. An Arrhenius acid is a hydrogen or hydronium producer, and it should say in there aqueous, and a base is a hydroxide producer. A Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. And finally, a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. That's a really great table that summarizes all three definitions. All right.